Are you really ready to keep paying hundreds every month just to survive the heat, knowing it can still fail you in one blackout? Because that's the reality for millions of Americans right now. Rising energy bills, overworked AC units, and nights where the air feels thick enough to choke your sleep. You're not just uncomfortable, you're trapped in a system that gets more expensive the hotter it gets. And here's the part that should stop you cold. I tested a setup that cost under $25, required no installation, no compressor, no ongoing power draw, and within minutes, the temperature shift was something you could feel on your skin, not a slight difference, a real drop. Now, before, understand this, most people who try it get absolutely nothing. No relief, no cooling, and they walk away thinking it's fake. But that failure isn't random. It comes down to one specific detail, one condition that almost nobody gets right. Miss it, and the system does nothing. Get it right, and it changes the entire outcome. So the real question isn't, does this work? It's why does it fail for most people and work almost perfectly for a few? And more importantly, can it work for you in your room with your constraints without wasting more money chasing solutions that don't hold up? Because in this video, I'm going to break down the exact mechanism, the exact setup, and the exact mistake that decides everything. But if you think this is just another trick, you're missing what actually makes it work. What you're looking at here is not a hack, not a trick, and definitely not one of those temporary life hacks that fades after 5 minutes. What you're dealing with is a real, measurable physical process that has been used for decades quietly because it doesn't need branding, it doesn't need a subscription, and it doesn't need you to keep paying for it. It just works if you understand it. And once you see the mechanism clearly, you'll realize something important. The cooling effect you felt isn't coming from a machine, it's coming from the material itself, pulling heat out of its surroundings. That's the key. This system doesn't blow cold air. It creates cold by absorbing heat directly from the environment around it. Now here's where it gets interesting. There are certain substances that, when they dissolve in water, don't release heat. They do the opposite. They absorb it, and not in a vague way, in a measurable, thermodynamic way. This process is called an endothermic reaction, and you've experienced it before. Whether you realize it or not, think about an instant cold pack, the kind you snap open when someone twists an ankle. Within seconds, it turns ice cold in your hands. No electricity, no refrigeration cycle, just chemistry pulling heat out of the water and the surrounding air. That exact same principle is what's happening here, but scaled up and directed in a way that affects the air around you. Not just the surface you're touching. When the compound dissolves, it requires energy to break its internal bonds, and that energy has to come from somewhere. So it pulls heat directly out of the water, and as that water cools, the air in contact with it cools as well. You're literally watching heat get removed from the system in real time. And here's the part. Most people never connect. When you combine that cold surface with controlled airflow, you're no longer dealing with a passive reaction. You're turning it into a functional cooling system. Not theoretical, not experimental, practical. And if the mechanism is this simple, this repeatable, and this effective, then the real question isn't whether it works. It's why you've never seen it used like this before. Now, hack when take a turn most people never see coming. This isn't new knowledge. It didn't just appear on the internet last year. The chemistry behind this has been documented, tested, and widely understood for over a century. So if it works, if it's simple, and if it's cheap, why isn't everyone using it? The answer isn't that it stopped working. It's that access to the most commonly used compound quietly changed after the mid-1990s. Certain chemicals known for strong endothermic reactions became heavily regulated due to security concerns. Not because of cooling, not because of agriculture, but because of entirely different applications. And when those restrictions came in, something unexpected happened. The everyday, small-scale uses disappeared with it. The cold packs stayed in medical kits. The industrial applications stayed in controlled environments. But the practical, at-home knowledge, the kind that people used, casually faded out of public awareness. No one banned the idea. No one erased the science. It just stopped being talked about. And over time, people forgot it was even an option. But here's the part that matters for you. Even today, most people who try to recreate this effect either use the wrong material or they use the right one in the wrong way, and when it fails, they assume the entire concept is flawed. That's the trap. The method didn't fail. The setup did. And that brings us right back to the question you should be asking yourself: are you missing the one detail that makes the difference between no effect and a measurable drop in temperature? But that's not even the most interesting. Because even if you understand the mechanism, you're still overlooking a version of this that is easier to access, cheaper to use, and in many cases, more effective. Here's the part. Almost nobody tells you the compound you've been hearing about isn't even the best option for this. Most people fixate on ammonium nitrate because it's what's used in commercial cold packs. But that's not what you should be looking at. There's another compound sitting on the shelf of almost every farm supply store in America that performs the same type of endothermic reaction, and in practical terms, it can deliver more usable cooling per dollar. It's called urea, labeled as 4600 fertilizer, and you've probably walked past it without ever realizing what it can actually do outside of agriculture. Now, here's why this matters. On paper, ammonium nitrate has a higher heat of dissolution per mole, which sounds impressive until you factor in molar mass and real-world cost. When you break it down per gram, per dollar, per usable setup, urea becomes a far more efficient way to generate a sustained cooling effect, and unlike ammonium nitrate, it's not heavily restricted. You don't need special access. You don't need to search for it. You can buy it for under $25 almost anywhere. That alone changes the equation. But the real discovery isn't just that urea works. It's that it behaves in a way that makes it more controllable, more gradual, and more adaptable to a room scale setup. This isn't about a quick temperature drop that disappears in seconds. It's about creating a cold surface that interacts with the air around you in a way you can actually use. And once you see that clearly, the idea stops sounding like a trick and starts looking like a system. But knowing it exists doesn't make your room any cooler. How you use it is what determines everything. So let's make this real, because this only works if you set it up exactly the right way. And every detail here has a purpose. You don't need anything complicated, but you do need the correct materials. One standard 2 0-inch box fan, one metal container, ideally a galvanized steel bucket or tub, not plastic, about 1 to 1.5 gallons of water, and roughly 1 pound of 4600 urea granules. That's it. Now picture this clearly. You fill the container about 2/3 full with water, not all the way, because you want maximum exposed surface area. That surface is where the cooling actually interacts with the air. More surface means more heat exchange, which means a stronger effect you can feel. Then you add the urea, but not all at once. You divide it into 3 stages. First portion goes in, you stir slowly for about 30 to 45 seconds. And then you wait, you let the reaction build, then you repeat. Second portion, stir, wait. Third portion, stir again. This staged approach matters because the cooling effect peaks shortly after each addition. So instead of one short burst, you stretch that cooling window over several minutes. Now, here's where the setup becomes critical. You place the fan so that the center of the blades lines up horizontally with the top of the water surface, not above, not pointing down, flat, level, and about 6 to 10 inches away. The airflow should skim directly across the surface, not blast into the container, because what you're trying to do is lift the cold air layer that forms above the water and push it into the room. If the fan is too high, you miss that layer. Too low, and you disrupt the surface without moving the cooled air effectively. Medium speed works best, not high, because you want the air to absorb that temperature drop. Not just rush past it. As the urea dissolves, you'll notice the water changes slightly in appearance, a bit denser. Slightly different how it reflects light. That's normal. That's the reaction happening. And within minutes, the water temperature will drop, and the air passing over it will follow You're not imagining it. You're redirecting heat out of the air in real time. But here's the problem. Most people follow something like this and still get no result. And when that happens, they assume the entire idea is flawed. But it's not. There's one specific mistake that completely shuts this system down, and almost everyone makes it. And that's exactly what we need to fix next. Here's the mistake that kills this entire setup. And once you see it, you can't unsee it. People aim the fan at the water, or straight into the container, or worse, they put the fan across the room and expect the cold to spread. That feels intuitive, but it's completely wrong. And the reason it fails comes down to one simple piece of physics that most people never think about. Cold air doesn't rise, it sinks. When the urea dissolves, the water cools, and right above that surface, a thin layer of colder, denser air forms. If you don't actively move that layer, it doesn't circulate through the room, it slides off the surface and pools on the floor, giving you nothing but slightly cooler ankles. That's why people try this and feel no difference. The system isn't broken, they're just not capturing the cold where it actually exists. The fan's job is not to cool the water further. The fan's job is to intercept that cold air layer at the exact moment it forms and throw it forward into the space you're in. That only happens when the airflow is perfectly horizontal. Skimming the surface, lifting that dense air before gravity pulls it down, tilt the fan down, you collapse the layer, aim it too high, you miss it entirely, put it too far away, and the air warms up before it reaches you. This is the difference between it does nothing and you can actually feel it working. And when I finally adjusted that one detail, when I aligned the airflow exactly where it needed to be, the result wasn't subtle. It changed immediately. When I realized this, everything shifted. And what happened next is the part that genuinely surprised me. I wanted to see if this was real. Not in theory, not in a lab, but in a situation that actually matters. So I set it up in a small room, about 280 square feet, no central air, no window unit, just a closed space holding heat the way most rooms do in the middle of summer. Outside, it was over 90 degrees. Inside, it was sitting at 86. That heavy kind of heat where the air doesn't move and every surface feels warm to the touch. The kind of heat you don't just feel, you carry. I measured everything before starting baseline locked in. Then I built the setup exactly the way I just showed you. Metal container, staged urea additions, fan aligned precisely at the water surface. At first, nothing dramatic, just the sound of the fan, the slight movement of air, but within the first couple of minutes, you start to notice something subtle. The air hitting your skin feels different, not colder in a sharp way, but less aggressive, less heavy. Then the numbers start to move. Around the 10 to 15 minute mark, the thermometer in the center of the room drops, not a fraction, not a rounding error, several degrees you can actually feel. And it's not just the number, the room changes, the pressure of the heat eases, the surfaces don't radiate the same warmth, you can breathe easier. By 30 minutes, the effect stabilizes, not freezing, not air-conditioned perfection, but noticeably, undeniably cooler than where it started. And what surprised me most wasn't just that it worked, it's how consistent it felt. Not a spike, not a quick drop and rebound, a sustained shift you could sit in, and in that moment, it stops being a concept, it stops being an experiment. It becomes something you can actually use, something that changes how the space feels around you. And when you put that next to the systems we've been told are the only real solution, the difference becomes impossible to ignore. And when you place it side by side with what we've been trained to think of as the standard, the gap becomes very clear. Now put that next to what you're used to calling real cooling. A standard window unit can cost $150 to $300 up front, plus installation limite, plus a steady pull on your electric bill every single hour it runs. Over time, that adds up to thousands of dollars just to maintain comfort. And the moment the power cuts, it gives you nothing. What you're looking at here is different, under $25 in materials, no installation, no dependency on continuous power, and in situations where traditional systems fail, rentals, outages, confined spaces. It still works. That alone changes how you think about it. But there's another layer most people miss. Once the cooling cycle is done, that urea solution doesn't become waste. It turns into a usable nitrogen source for soil, something people literally pay for in lawn care. So you're not just cooling your space, you're repurposing the same material for something else. Zero waste. Two functions. One, cost. But like any physical system, it has limits you need to understand. But this is where most people either overhype it or misunderstand it completely. This system does not ignore your environment. It responds to it. And the biggest variable you need to respect is humidity. In dry climates, places like Arizona, Nevada, parts of Texas, the air has room to absorb more moisture, which means as that cooled water surface sits there, you get a second layer of cooling from evaporation. Chemical cooling plus evaporative cooling working together, that's when the effect feels stronger, faster, and more noticeable. But if you're in a humid environment, Florida, the Gulf Coast, anywhere, the air already feels heavy. That second layer almost disappears. The chemistry still works, the water still cools, but the air around it can't carry away additional heat as efficiently, so the result feels softer, less dramatic. That doesn't mean it failed. It means the system is behaving exactly the way physics says it should. And there are other factors too: room size, airflow obstruction, starting water temperature. All of them shape the final outcome. This is not magic. It's a system with conditions, and once you accept that, you stop expecting perfection and start understanding performance. And when you understand those limits clearly, you begin to see the bigger picture. Here's the part that stays with you after everything else fades. The most useful knowledge isn't always the most visible. It's the knowledge that doesn't generate ongoing profit. Systems that require installation, maintenance, and monthly payments get promoted. Simple. Repeatable solutions that end the transaction quickly don't. So they don't disappear because they stop working. They disappear because no one is incentivized to keep them in front of you. That's how practical knowledge becomes hidden without ever being secret. And once you recognize that pattern, you start questioning what else you've been taught to overlook. And that leads to a much bigger question. You just saw a system that can shift the feel of a room with under $25. No compressor, no install, no ongoing cost. And it works because of a 200-year-old principle you can test tonight. If you set it up right, you already know what to expect. If you don't, you know exactly why it fails. But here's the part. Most people still miss cooling. The air is only half the battle. The biggest heat load is often coming through your windows. And if you don't address that, you're fighting a losing game. So the real question is, what's the simplest way to stop that heat before it ever gets inside?